Okay, so I've got H2O2 and I've got another chemical, and right now they do react. It's spontaneous. Okay, H2O2 is breaking down into O2 and water gas, so 2 molecules of H2O2, 2 particles are becoming 3 particles. 1 O2 and then 2 water molecule gases. So it's spontaneous. We know it gives off heat. So I know the surroundings are entropy is going to increase, and internally the system is going to increase. So therefore, totally the delta S of the universe is what? Is positive. So this is spontaneous. This is exergonic or endergonic? Exergonic. This is spontaneous, yet we look at it and say, it looks like I have to add work to this. Okay, remember, spontaneity is a pathway that's allowable. Gasoline sitting in a gas can is spontaneous. Will spontaneously react with oxygen. We still say its delta G is negative, but you need to start the reaction. Well, here, the energy barrier is so high that although it's warm, okay, and there's collisions, those collisions are not effective because what's missing? Probably if it's biological, the orientation isn't right. So, like an enzyme, I'm going to add a catalyst that's going to lower the activation energy. Now, like a catalyst or like a biological enzyme, what's going to happen is it's going to help with the orientation, lower the activation energy, and the amount of heat in this is enough to get over that little hump now, okay? And of course, the rate of reaction is going to increase probably over 1,000 times, okay? So watch what happens. I'm adding a catalyst, and it's a chemical catalyst, but it works by the same principle as a biological one. Okay, now you saw some fizzing. That fizzing is the O2 being made. Now it's going to steadily increase, okay? And what's cool about this reaction, look at the level. And look at my line up there. It's exergonic, therefore the delta G is going to start high and go what? So this is going to show us the pathway. Before I can go from low, I have to have a what? An energy barrier. So this green monster is cool because now we're climbing up that energy barrier. Here it is, the green monster. We're at the what? What's the top of the tip of the apex? What do we call that in this diagram?
The
activated complex. And then of course, all of a sudden, it goes down. Now look how it's lower now.
What?
Look how it's lower, just up there. It went from high to low.
What?
It's exergonic, and the green monster was the apex of the activated complex. That's why I like it. Now, in truth, if this is, I was very lucky with the snap, by the way.
Yeah, what?
Okay.
That was so weird.
All right. In any case, the point is, do catalysts, this is important, even though this wasn't a biological catalyst, people think, oh, catalysts are one and done. No. If I collect the substrate in my 3-dimensional arrangement of my protein, and once they bond, they go off, I'm ready for what? More substrate. These guys are used over and over and over. So remember, to increase the rate of reaction, we need more catalysts, but the important part about catalysts is that they're not ever going to be consumed in the reaction. So if I was to add more catalyst, okay, now a lot of it's spilled over, so I'm sorry, if I was to add more of the reactant, okay, because the catalyst is still there, notice the color? So if I add more reactant, it should start going again, if I have more. Yep, and it's doing it again. And the reason why it's doing it is because a catalyst or an enzyme in a chemical reaction is never consumed by the reaction. They're able to be used over and over and over again. And chemistry will show that catalysts, chemical catalysts, get reproduced at the end of a multiple step process. So there is the green monster. It parallels a potential energy curve perfectly. Okay? And of course you watch me control it.
That's so cool.